guys. Hi.
Okay, seeing as how it's right about 8 o'clock, and I think we're all set, ready to go with the broadcast and everything. So, good evening. Welcome to the Hubble Space Telescope Public Lecture Series. Can you hear me?
Yeah.
Okay. My name is Zolt Levay. I'm filling in. As you may have realized, I'm not Frank Summers, the usual host tonight. There's a big meeting, an astronomy meeting going on this week in Boston, American Astronomical Society. So a lot of people from here are up there. And Frank asked me to fill in since I'm one of the few remaining people here at the Institute this week. So anyway, we'll get started. As usual, I'll introduce the speaker in a few moments, have some introductory material here. First of all, the next couple of lectures, as you can see, in July, we'll have Andrea Bonzetti from Space Telescope right here, talking about building new worlds in protoplanetary disks. Right about 8 o'clock. In August, on August 5th, we'll have Jennifer Lotz, also from the Institute here. Good evening. Talking about the Frontier Fields, which is an exciting new project that's just getting started here. A sneak peek at the first billion years of the universe. That'd be a good talk. My name is Zolt Levay. I'll remind you that these talks and lots of other things are available. Usual host on our website. There's a big meeting, astronomy meeting going on this week in Boston. You can sign up for email notifications for this lecture and for some other topics if you send a note to the email address you see up there. We promise we won't spam you, but we will send you some interesting stuff related to these sorts of events. And unfortunately, I've been told that the weather may be kind of iffy later on tonight. So whereas usually the observatory across the street at Johns Hopkins at the Maryland Space Grant Observatory, they usually open up for observing after the talk. Tonight, they decided not to open up because there's a chance of some stormy weather in the area. So I'm sorry about that. And just Frank wanted me to just give a couple of news notes from recent exciting events from the world of astronomy. One of the more exciting things we've done lately, it's not about a kid's reading primer. The spot here refers to the Great Red Spot on Jupiter. Jupiter, of course, is one of the planets in our solar system. It's the largest planet in our solar system. And it has this feature on it called the Great Red Spot. This image is from the Voyager spacecraft, which flew by Jupiter way back in 1979, and took this fabulous image of the Great Red Spot and a lot of other stuff going on. So for a little bit of context, here's an image of the Earth to scale with the Great Red Spot, and that might give you some idea of how great this Great Red Spot is. The name is kind of a fanciful name, Great Red Spot. Well, it's great because it's large. As you can see, it's larger than the Earth. Of course, Jupiter is much larger than the Earth. It's about 11 times the diameter of the Earth, so about 1,000 Earths could fit inside Jupiter if you could fit things inside of Jupiter. Jupiter, of course, is almost all gas, and hey, that's a great topic for tonight. Our speaker will be talking about gas in the universe, but Jupiter is a gaseous planet, so it's almost entirely gas. What you see in the atmosphere is all atmospheric features, clouds, weather, just like we have on the Earth. This is a very violent storm that's been raging in Jupiter's atmosphere for a long time. In fact, it's been observed as far back as 300 or 400 years ago. This is a drawing by the famous astronomer Cassini done in 1677. And that black spot on there is probably the Great Red Spot. So we think it's been around at least that long. More recently, of course, people have been observing it, Jupiter a lot, and in particular the red spot's been pretty continuously monitored for about 150 years. During most of that time, it's remained pretty much the same. Very recently, In about 2012, a lot of amateur astronomers that were observing Jupiter noticed that the red spot seems to be getting smaller. And actually, it's been observed to be shrinking gradually over the last quite a while, but recently that shrinkage has seemed to accelerate. And it's shrinking, and it's also changing its shape. So the shrinkage is mostly along the long dimension there, so it's becoming rounder, as you can see in this series of images. These are very recent images from Hubble. The whole disk of Jupiter with the beautiful red spot taken on April 21st. And then these other images are other images that Hubble took from 1995, 2000, and 2009. And you can pretty clearly see that the spot is indeed getting smaller. Now the big question, of course, is why is it doing this? And unfortunately, the answer is nobody really knows. Most of the experts don't really have an explanation. Amy Simon, who is the astronomer who was leading the Hubble observations, speculated that it may have something to do with the very turbulent material around here and little eddies maybe interacting with edges of the red spot and causing some strange stuff to go on, but nobody's really sure. So this is a kind of an interesting area where people are still doing very actively trying to figure out what's going on in a place like this. It's very close to us. I mean, Jupiter in the cosmic sense is just in our backyard, so it's kind of interesting that we don't know everything there is to know about Jupiter and the weather on Jupiter yet. So that was a kind of interesting thing that came up not too long ago. So without further ado, I'd like to introduce our talk tonight. So gaseous states of matter play a prominent role throughout the universe. Not to mention in our everyday lives. We breathe the air in our atmosphere all the time. It's a gas. From the atmospheres of planets and stars to the vast expanses of interstellar and intergalactic space. Gas clouds are also critical to the formation and development of stars and the life cycle of galaxies. Tonight, Dr. Andrew Fox will describe observations of light emitted by in these various environments, which is our only source of information for most of our knowledge of the universe. Dr. Andrew Fox is on the staff here at Space Telescope Science Institute. He received his PhD from the University of Wisconsin at Madison in 2005. Before joining STSCI as a European Space Agency astronomer in 2011, he held postdoctoral fellowships in Paris, Santiago, and Cambridge, the UK Cambridge, I assume. He's interested in the mechanics by which galaxies feed their star formation, in particular in the Milky Way, our own galaxy, where these processes can be viewed in great detail. Andrew.
Okay, thank you, Zolt. And it's a pleasure to be here and to see so many people out there in the audience. This is going to be a talk about the gaseous universe, and the idea here is to do a tour of different places that we can observe with our telescopes and to show to you that gaseous matter, the same kinds of gas that we can observe in the lab and in the atmosphere of the Earth, are also seen in other places in the universe. And the knowledge that we have of gases here on planet Earth is vital for us to understand the gases that we observe in many, many different places in astronomy. So I want to start with some very basic ideas about what gas is. When you think of gas, you might think of the natural gas that comes out of your stovetop. You might think about how expensive it is to fill up your car at the pump, but of course this kind of gas, that's short for gasoline, that's a liquid. That's not really the gas that we mean in the scientific sense of the word. So as you may remember, there are several basic states of matter. We're often taught that there are three: solids, liquids, and gases. In fact, nowadays it's more common you'll see people talk about four phases of matter, with plasma, which is an ionized form of gas where the atoms have been split into nuclei and electrons. Now, plasma is treated as a separate category. So as you go from solids to across to plasma in this representation, the idea with solids is you have a material that has a fixed volume and a fixed shape. A liquid has a fixed volume, but its shape will change depending on what container it's in, whereas a gas has no fixed volume or no fixed shape. It will just fill whatever container that it's in. Now, when it comes to gases in astronomy, we have some pretty big containers. I mean, the Milky Way, the halo of the Milky Way, the space between galaxies, these are enormous volumes. So gases fill enormous volumes of space, and that's something I'm going to be coming back to throughout this talk. Matter changes between these phases by the addition of heat. So if something gets hotter and hotter, you'll go from solid to liquid to gas and eventually to plasma. And plasma is where you've injected so much heat into the matter that the electrons are no longer bound to the nuclei of those atoms. And we're going to come across plasma in many places in this talk. So one of the reasons that gas is worth studying, as we see it in many different places, is also very well understood from the point of view of physics. We understand how and why gas emits radiation, and how and why gas absorbs radiation. We can study these things in the lab, and so we can see the same processes happening in astronomy. And it's not just a science that you can do at visible wavelengths that your eye can see. You can study gases all across the spectrum using X-rays and using radio waves and microwaves and many different wavelengths that are a part of the toolkit of modern astronomy. You might wonder, why do I have a picture of a neon sign up here? So a neon sign is a good example of a case where a certain type of atom, a neon atom, is excited by injecting energy into it, and it emits radiation at a very particular wavelength or frequency, and that's the wavelength corresponding to red light. So the parallel with astronomy here is that we can use the colors of light emitted from different places in the universe to identify which chemical elements are present, just like the red of a neon sign tells you something about what chemical elements are present inside it. One other saying that you might have heard of this, nature abhors a vacuum. This is first attributed to Aristotle, the philosopher. The basic idea that people have when they apply this is the reason that you won't find a complete vacuum in physics is that if you had a region of space that didn't have any atoms or molecules in it, then whatever was next to it would just simply diffuse over, and some of those particles would spread into it and fill that region. And that physical principle is basically very valid to astronomy, just as it is here on Earth. So let's start in the Earth's atmosphere. This is a great place where we know about gas. Most of the molecules in the Earth's atmosphere are either nitrogen or oxygen. There's a little bit of argon and carbon dioxide there. The atmosphere is actually pretty thin. It's only about 100 kilometers thick, depending on exactly how you define it. But just for comparison, the radius of the Earth is about 6,000 kilometers. And you just have this thin 100-kilometer layer of gas on the surface of it. Of course, that's vital for life on Earth. Our oxygen we breathe is in that atmosphere. There's a tiny amount of ozone. That's the O3 at the end of that list. That ozone is also very important for us because it blocks some of the harmful UV radiation from the sun. So the atmosphere is a critical part of a planet like our own. Now, Zolt already showed you what's been happening recently in the atmosphere of Jupiter, this gas giant planet in our own solar system. This is a planet like Saturn and Uranus and Neptune that has no solid surface. It's pure gas, at least all the way down to perhaps its core. The composition of the atmosphere of Jupiter, though, is different from the atmosphere of the Earth. Here, most of the atoms that are, the particles that exist are hydrogen and helium. There's little bits of methane and ammonia, and the different compositions of the elements in the different planets actually help to explain the different colors, for example, of Neptune and Saturn versus Jupiter. But this is the same series of pictures showing you the shrinking Great Red Spot, which has left a lot of people scratching their heads recently. Well, let's go outside the solar system to another planet that was observed with the Hubble Space Telescope. And this is the planet called HD 209458b. If you're really interested, what that means, it's the 209,458th star in the catalog of Henry Draper. His initials were HD, and he was a famous astronomer who cataloged this enormous list of stars so that people could come and identify them and find where they are in the sky. So this is a star that happens to have a planet going around it. And when that planet moves in front of the face of the star, which is called a transit, two very interesting things happen. First of all, you block some of the light from the star so that the brightness of that star's radiation goes down. And secondly, because that planet has an atmosphere, you not only block the light from the star, you also absorb very specific wavelengths of light. And that tells you about what chemicals exist in the atmosphere of that planet. And it turns out that when they studied the light that had passed through the atmosphere of that planet, they found the signature of hydrogen gas that was in the atmosphere of that planet. This was the first planetary atmosphere outside our solar system. We call that an exoplanet atmosphere, discovered by the Hubble Space Telescope. This is an artist's impression. No one is able to take a high-resolution image of what it looks like. But it's using a technique called spectroscopy, where you take the light from a star and you split it up into different colors, and then you analyze how much light there is at different colors. That's how you can do this, and you can figure out what is the actual composition of the atmosphere. Now, as I've already said, I mean, gas is everywhere in astronomy. One place that's often thought about when people talk about gaseous clouds is in so-called nebulae. I mean, nebulae are very attractive objects. There are a lot of images that have been taken, for example, with the Hubble telescope, of these types of objects, and they're basically big clouds of gas that exist between the stars and galaxies. And these clouds are the places where new stars are formed, and they're also places where stars release their elements when the stars get to the end of their lifetime. So on the left here, this is a famous nebula called the Butterfly Nebula. That's actually a type of nebula, a planetary nebula, which is what happens to a star at the end of its life. On the right, this is a very famous image from the Hubble telescope called the Mystic Mountain. This is a star-forming nebulae where we can see new stars being formed out of that gas. This was released on the 20th anniversary of the Hubble Space Telescope. But there's a very close link between the gas and the stars that form out of it, and that I'm going to come back to throughout this. Now, sometimes you hear people say that galaxies are basically made of stars and gas. Well, the thing is that stars themselves are gaseous objects. What is a star? Well, a star is, to a very good approximation, a spherical ball of plasma, which is an ionized gas, that's held together because gravity is pulling it in towards the center, and gas pressure, the pressure of all the particles in the gas, is holding it up. So stars are in some ways similar to the gas that's in nebulae in between the stars. It's still gas that's there. It just happens to have a very different temperature and a very different density. So in addition to all the stars that we have in a galaxy, in the Milky Way there are something like 100 billion or so, there's a lot of gas that exists between the stars. And I'm not just talking about the nebulae that I showed you already. I'm talking about a very widespread, diffuse layer of gas that exists everywhere in the disk of our galaxy, in the plane of our galaxy. And the reason we know there's gas there is from observations at radio wavelengths. So this is a map of the entire sky taken at a wavelength of 21 centimeters. So if you have a radio telescope and you look at a wavelength of 21 centimeters, you make an all-sky map. This is what you find. You find this narrow strip of emission right along the center of the map there, and then it's much fainter above and below. And that's telling you that everywhere throughout the galaxy, between stars, there is a gas, a neutral hydrogen gas, and that gas is emitting these radio waves that we can use to measure how extended that gas is. So now I want to show you a couple of numbers just to give you a feel of how these different places compare when we stack them against each other. Now, if you want to describe a gas, there are two numbers, the density and the temperature, that tell you a lot about what's happening. The temperature, of course, is how hot something is, and the density is a measure of how many particles you have per unit volume. So we often do that per cubic centimeter, Okay, how many particles do you have in each cubic centimeter of space? Now, if you start in the atmosphere of the Earth, just take a point at sea level, typical temperature, of course it varies, but on average, if it's, say, 62 degrees Fahrenheit, that corresponds to 290 Kelvin, which is the temperature scale we use in astronomy. If you look at the density of the density of air in the Earth's atmosphere, okay, you find that 1 cubic centimeter of air contains something like 5 times 10 to the 19 particles, mostly nitrogen molecules. That's 50 billion particles, all right? And 1 cubic centimeter is about the volume under the tip of your thumb. So it's amazing to think, even though air seems like it doesn't really have much in it, that region of the air, which has the same volume as the tip of your thumb, it contains about 50 billion particles. What happens if you go to the surface of the sun? That's much hotter, almost 6,000 degrees Kelvin. And it turns out the density there, it's only known kind of approximately, but it's several orders of magnitude, several times lower than it is in the Earth's atmosphere. But if you were to go to the core of the sun, where energy is being produced by nuclear fusion reactions, the temperature is an enormous 50 million degrees, and the density is as high as 10 to the 26. Now, these are all gases or plasmas, but you can just see the huge variety you get between the different places. We can add a couple more lines to this table if we go to interstellar space. I showed you that radio emission from the interstellar space. There, the temperature is pretty warm. It's about 10,000 Kelvin, but the average density is about 1. You have 1 particle per cubic centimeter of interstellar space on average in our galaxy. So what's the difference between the gas in a star and the gas in interstellar space? It's 26 orders of magnitude. So it's 1 with 26 zeros after it. Now, if you go to the intergalactic space between galaxies, the densities are several orders of magnitude lower still, even though the temperature is about the same. So we see this enormous range in what the density of gases is in different places of the universe. Okay, the next thing I want to talk about is our own Milky Way. This is a picture of the center of the Milky Way. Those of you who are amateur astronomers will know this is in Sagittarius. What you're seeing when you look at the center of the Milky Way is all the stars that are unresolved. We can hardly separate them. They form this white glow in the background. And then on top of that, you have the dust lanes, the brown clouds that block the light from the stars behind. It turns out that beyond the Milky Way, there's only 3 galaxies that you can actually observe with the naked eye. 2 of them are the so-called Magellanic Clouds. The large Magellanic Cloud, which is in the top right of this image, and the small Magellanic Cloud that is down here. And this is an optical view. So this is what you see if you look at the Magellanic Clouds with the visible light, okay? Now, the Magellanic Clouds were named after the famous explorer Ferdinand Magellan, who is well known for leading the first circumnavigation of the Earth. In fact, in a few years, we're going to come up on the 500th anniversary of that journey around the Earth. He didn't make it all the way around. He actually died in the Philippines before he got back to Europe, but then the rest of his crew continued the tour and brought his ship back home. But the Magellanic Clouds were named after him, and the name has stuck ever since. Now, compared to the Milky Way, these clouds are pretty small. I mentioned the Milky Way has about 100 billion stars. The Large Magellanic Cloud has something like 3 billion, and the Small Magellanic Cloud has 300 million. In terms of distances, you may be familiar with light years, how many years it's taken the light to travel to us from those galaxies. You're talking about 160,000 or so for the Large Magellanic Cloud, almost 200,000 for the Small Magellanic Cloud. Those numbers look huge, but in terms of how far away most galaxies are, these are really close by. These are in our backyard. Now, what happens if you look at these objects with different wavelengths? So let's say we take a radio telescope. This is actually an array of radio telescopes down in Australia Telescope Compact Array. If you look at the Magellanic Clouds with something like that, you're going to see a very different picture. This is an idea of what the gas in the Magellanic Cloud, the Large Magellanic Cloud, the LMC, looks like in radio emission. You can see all this very detailed structure, all these clumps, all these gaps in the gas. And this is the brightest parts where there are the highest concentrations of gas. That's where you're going to get new stars forming. Now there's another thing you can do, which is you can say, well, let's put the radio emission on the same scale as this map. So instead of using optical light, I'm just going to put the exact same region of the sky and show what does the radio light look like. When you do that, this is what it looks like. The really neat thing here is that the gas that you see in the radio emission actually covers much more space than the stars do, right? So if I go back to the stars quickly, they're much more confined. The gas is more extended, and there's even a bridge of gas between the two Magellanic Clouds. They're connected. So there's a common envelope of material between them, and you wouldn't have known anything about that if you hadn't been able to look at radio wavelengths. That's called the Magellanic Bridge. Now, not only is there this envelope between the clouds, it turns out that there's a huge stream of gas behind the Magellanic Clouds as they orbit the Milky Way, because these two galaxies are falling around the Milky Way. They're in the gravitational field of our own Milky Way galaxy. And as they come in towards the Milky Way, they're producing a huge stream of gas, which is called the Magellanic Stream. Now, this is another all-sky map where you've got the disk of the Milky Way along the center. So along the equator, the white glow that you can see there is the starlight from our own galaxy. This is where the Magellanic Clouds are over here, the SMC and the LMC for the small and the large. And what we see in radio light is this enormous tail of material that comes all the way down through the South Pole and up to the other side of the galaxy. And it also continues up in front of the clouds. Now, just to give you an idea of how big that is, I can put the continents of the Earth on the same scale, because we measure longitude and latitude to measure where things are on a map on the surface of our planet. In astronomy, we do the same thing for the galaxy. We have galactic longitude and galactic latitude. Why am I doing this? I'm just showing you how there is an enormous stream of gas that covers about half of the entire sky. You can see, if you compare it to where the continents are, you've got the Magellanic Clouds down there in the Indian Ocean somewhere, and the stream comes through Antarctica and all the way up the coast of South America. It's enormous. If you were to look outside of our galaxy and look back towards us, you might see something like this. You've got the two Magellanic Clouds shown there that are losing huge amounts of gas, and this Magellanic Stream is just extending behind them. And as I said, they're responding to the gravity of the Milky Way. What's going to happen to all this gas is eventually it will be able to accumulate and fall onto the Milky Way. So the Milky Way is the big winner in all of this. These two little dwarf galaxies are being stripped of the gas that they have, and that gas is going to end up coming into our own galaxy, where it may eventually be able to form stars. Let's move out a little bit further. I mentioned there are only 3 objects you can see with the naked eye outside the Milky Way, and 2 of them were the Magellanic Clouds. The third is Andromeda, the great Andromeda galaxy. I'm showing the full moon there for scale. The full moon is about half a degree across. You can see that this this galaxy is huge, several degrees, although with the naked eye you won't see anything like that. This obviously needs a big telescope to bring out the structure. But this is now known to be at a distance of about 2.5 million light years. Now, the person who really was the first to understand how distant the Andromeda galaxy was Edwin Hubble, the man who our Hubble Space Telescope is named after. And he was able to make the first distance estimate to the Andromeda galaxy. And he did that using a telescope called the Hooker telescope, the 100-inch Hooker telescope, which is in California. And it's interesting that this is a 2.5 meter telescope. The Hubble Space Telescope, named after him, is 2.4 meters. It's actually pretty close. But he was able to measure the distance to Andromeda, and that settled a really big debate that was going on in the 1920s. It was called the Great Debate, because back then, people had observed nebulae, as they call them, like this, but they didn't know, was that something in our own galaxy, or was that outside the Milky Way? Was it an entirely separate object? And Hubble was the one who actually settled that, because when he measured a distance to Andromeda, and he did that using a certain type of star called a Cepheid variable star, by measuring how quickly those pulsated, he was able to measure the distance to the galaxy. He found that the distance was about 900,000 light years. That was the number that he published on the distance to this galaxy. Well, 900,000 light years is way bigger than our own galaxy. So he realized that this couldn't fit inside the Milky Way. This had to be more distant than that. So we couldn't think of the Milky Way as the center of the universe. It showed that there are other galaxies out there. It turns out that Andromeda is actually more massive and bigger than the Milky Way. So this was very important for putting our galaxy in context. Just one last point. We now know that the value of the distance to Andromeda, is about 2.5 million light years. So it's a factor of 2 or 3 higher than the number that he had, to do with different calibrations for the way he was measuring distance. But the main point is that he found that this was certainly far enough away to be outside the Milky Way. Now we can see that between Andromeda, which is on the top right there, and its neighbor, which is called M33, there is a bridge of material, just like there was a bridge of material between the Magellanic Clouds. And this was discovered quite recently in radio emission. Exactly where that gas comes from isn't completely known. It may be falling onto the galaxy and onto Andromeda for the first time, allowing it to form new stars. So I want to come back to this idea about gas in astronomy as fuel for new stars, for star formation. Because just as you'll put gas in your car and you'll get motion out of it, you can put gas in the form of interstellar gas into a galaxy and you'll form new stars. Okay, that's the idea I have about fueling a galaxy from gas. Now, there are cycles that go on within galaxies where new stars form out of interstellar gas, and once they get to the end of their life, they can return the gas back into the space around them. But the gas that's been cycled through stars is different than the gas that they formed out of. And the main difference is that the composition, the chemical elements that make up that gas have changed because the stars have produced new elements. All the chemical elements that we study and we put in a periodic table that a chemist would show you are ultimately synthesized in the cores of the central cores of stars. Now, astronomers like to make simplifications, and sometimes you'll see an astronomer turn a periodic table into something like this. Everything from lithium up, which is the third element up in the periodic table, they'll just refer to as metals or heavy elements. So you've got hydrogen, the first element, you've got helium, the second element, those are the two at the top, and then everything else is referred to as metals. Now you might say, why? How on earth can you do that? The reason is that hydrogen and helium are thought to be produced very early on in the universe, right after the Big Bang. All the hydrogen and helium atoms were synthesized at that time. But everything else that's called metals here is mostly produced, I say everything, but some of the lithium and boron might have been produced earlier on, but to a very good approximation, all the other elements come from the cores of massive stars. And this is studied by people who look at stellar evolution, the way that stars change as time goes on and they run out of fuel. And this is a picture showing you a slice through what a massive star will look like at the end of its life. You have these different rings of material or shells of material that have a different chemical composition. Now when I say a massive star, this is a star that's about 10 times more massive than the Sun. And it's gone through various stages where it's burned through different types of fuel. So to start out with, the star will burn hydrogen fuel. Our Sun right now is burning hydrogen fuel. When the hydrogen runs out, it will move on to helium. And if the star is massive enough, it will move on to a whole series of different elements until you end up with something like this. And this is where the chemical elements are thought to be produced, in the cores of these stars. When a star gets to the end of its life and all the iron in the core has been processed, you can get a supernova. That's where the star explodes and releases a lot of these elements out into interstellar space. And eventually, across the galaxy, where planets can form and new stars can form and so on. Now, that's not the only type of supernova. This is what you would call a core collapse supernova from an individual massive star. There's another type of supernovae which is called a type 1a supernovae. This happens when you have a binary system. Here you've got a white dwarf star. It's a very dense star on one side, and it's pulling material off a companion. And if it pulls enough material across onto the white dwarf, you can get an explosion that will be visible to very large distances because it's very bright. And you can also produce elements such as iron through this channel as well. So supernovae will produce elements, but if you want to get these elements out into the regions between galaxies, you need a process that can do that for you. And there's something called a galactic wind that will take material that is being produced in the disk of a galaxy and can throw it out into the intergalactic space. This is a very famous picture of a nearby starburst galaxy called M82. The starburst galaxy is one that's forming stars much more rapidly than a galaxy like the Milky Way is. So there's lots of new star formation going on all the time. And you can see from the central region of this galaxy, you have these huge conical outflows that are getting out into space, driven by, it's debated about how much of that is driven by supernovae and how much of that is actually driven by a supermassive black hole that's in the middle of the galaxy that is also putting energy into its environment and throwing out material out of the galaxy. So, in the last part of my talk, I want to move to the more distant universe. I've talked about nearby galaxies mostly up to now. How can we detect gas very far away, particularly where radio telescopes aren't going to work anymore because the emission is too faint? Well, one technique that people spend a lot of time doing here at the Space Telescope Institute, for example, is a technique called quasar absorption line spectroscopy. Now that sounds pretty complicated, but in fact what you're doing here is it's quite straightforward. You're taking a very bright source of light, think of it like a lighthouse, and you're seeing what happens to that light when you split it up into all the different colors of the spectrum, all the different colors of the rainbow, if you like. So here's an example where you're looking at a quasar and your line of sight from your telescope happens to pass through 3 different clouds between us and the quasar in the background. Now, each of those clouds is a gas, and we know that gas can absorb light at very particular wavelengths. So each of these clouds leaves a certain signature in the spectrum of that quasar. So the first cloud can leave a line in the spectrum here, which is called, we'll label A. The second cloud will leave a line at this position, and the third cloud will leave a line there. So what you're actually left with when you observe this is a series of lines that contain information about what's the chemical composition of each of these clouds. So this is the technique that people use to study the halos of galaxies out to very, very high distances. Because it turns out that when we see these gas clouds in front of the quasar, what we're often seeing is the very extended halos of individual galaxies. The galaxies have these very faint but large halos that give you this absorption signal, even though you can't see the stars there. And so you can't see them shining at you. You have to detect them through these other methods. Now, what if you go to even bigger scales? There is a term called the cosmic web, which describes what, on really large scales, astronomers think that the universe looks like. This image is actually a computer simulation of what the gas in the universe looks like in a box where each side of that box is 30 million light years in size. Okay, so this is an enormous volume of space. And you can see this filamentary structure, right? The green is the gas in the universe, and in in the center of all these filaments, you get the what you might call the nodes of the cosmic web. Those are where the galaxies form and the clusters of galaxies form. But this is a prediction of what the gas in the universe would look like on that large scale. So how can we test the prediction and go out and look for it? We can do the quasar absorption line experiment, and we can see if we can detect that gas in absorption. And this is how you would do it. You would look for something called the Lyman alpha forest. And the Lyman alpha forest is saying that, okay, if I take a sight line that passes through all these green clouds, I should get lots and lots of features in my spectrum, each one corresponding to one of the features of the forest, or of the gas. And that's exactly what we see when we look at very, very distant quasars. We take the light from the quasar, and we plot it as brightness against wavelength. Now, if you look at a nearby quasar, what you'll get when you look at a spectrum is something like this. There aren't that many dips and features in the spectrum. If you go to a distant quasar, much further away, you see this huge forest of lines. There's just a very large number of dips in the spectrum. And each of those corresponds to one of the filaments of gas in the Lyman alpha forest. So by counting how many of those there are, measuring their properties, we can actually learn something observationally about that gas. What about if we go back even further to the early universe? The first time that a gas is thought to have formed in the universe is when the universe was about 380,000 years old. And this is a time called recombination. Before this is 380,000 years after the Big Bang, the universe was very hot. And it was so hot that the material existed as plasma. That is to say, the electrons, which are in green here, were not bound to the nuclei, which are in red. It was too hot. The gas just couldn't stay bound, so it was a plasma. But the universe was expanding, and as it expanded, it was cooling down. And eventually it cooled down to a point where neutral atoms were able to form. So instead of having this plasma, you had a gas. You went from a situation where the universe was opaque and light couldn't travel through it to where you had a transparent gas which light could pass through. And that's called recombination. Now, how do we know that? Again, I want to come back to the evidence we have for each of these physical ideas. The answer is we can see the light that was emitted from that epoch of recombination. And we see it in the form of the cosmic microwave background. This is what the night sky looks like if you look at it in microwaves. This radiation came from that epoch, about 380,000 years after the Big Bang, when the first gas formed, when the plasma recombined to form a neutral gas. And you'll see it referred to as the oldest form of light in the universe. Now, what happened after that? Well, the universe didn't stay neutral forever. Right after recombination, the first thing that happened was a period called the Dark Ages. We don't know much about the universe in the Dark Ages because there weren't many sources of light. But at one point after that, the first galaxies and the first quasars began to switch on. And quasars are the cores of the galaxies where a lot of radiation is emitted. Now, when those galaxies and quasars switch on, they start to shine into bubbles of space around them. They ionize the gas around them. And so you're producing these bubbles of gas. And eventually, as time passes further than that, the bubbles start to overlap, and you reach a point where all of the space between galaxies, all the intergalactic space, is ionized. So this whole process is called reionization. So the universe started out ionized very early on, and then it became neutral, and then when the galaxies switched on, it became ionized again. So you have this trend going from neutral to ionized as cosmic time has progressed. So just before I finish up here, I wanted to mention that one other reason that we're interested in gases is that most atoms in the universe are in gases. Compared to all these different forms of astronomical matter I've shown you, solids and liquids really account for a very small fraction of all the regular matter that exists in the universe. So with that, I'm going to end, and I'm going to put up this picture of the so-called Monkey Head Nebula that was released earlier this year, and ask you if you have any questions. So thanks for your attention.
Andrew, that was a great presentation. Open it up to questions.
Yes?
You said that the interstellar gas has a very high temperature.
Yes.
I wish you could say some more about that. It says to me that out there in space it's hot.
That's right. So interstellar gas can be heated to high temperatures around 10,000 Kelvin or so, and it's mostly heated by starlight. So there are ultraviolet radiation, ultraviolet photons that come off stars that can heat the gas that's present in interstellar space. And the temperature that it has is set by a balance between how much heating you have and how much cooling you have. Now, saying that, there are regions of interstellar space that are cooler. So the nebulae that new stars form out of are much colder than that. You need cold gas to be able to shrink down in what we call a molecular cloud and eventually form a star. But most of the volume of the space in between stars is filled with this diffuse material that has a temperature around 10,000 Kelvin or so.
I would like to follow that up.
Yeah,
You showed us numbers,
right.
and in the space between the nebulae, the number said there was one particle in 100 cubic meters.
One.
That was the number, I believe. Maybe it was 10. You flashed up. But it looked like one particle, 0.4 or 50 is 1.
Ah, yeah, for intergalactic. That's right. Yes.
Okay. How can you talk about temperature when you have one particle in 10 or 100
Because temperature is vibration.
So the reason you can talk about temperature is you can measure the temperature of an astronomical gas, even if the density is extremely low. And we have ways of measuring the temperature by looking at the width of absorption lines that come from these spectroscopy experiments. So if you look at one of these lines, like these hydrogen lines, and you look at how broad it is, that tells you what the temperature of the gas is. The hotter the gas, the broader the line that you'll see in your spectrum is. If a cloud is very cool, you get a very narrow component because there isn't much motion of the atoms that are giving you the absorption. So we make measurements that actually tell you what that temperature is. It's a measurement rather than some sort of estimate.
I'm only a naive physicist, but my belief is that temperature is a statement of the velocity of the particles. And if you only
Yeah.
have one, I'm trying to find out what the meaning
Well,
of temperature
right. So I see what you're saying, but you only have one per cubic meter or so. But remember, intergalactic space has a lot of cubic meters. So we can study a cloud that might have a size of, 10,000 light years or something, or 100,000 light years. If you turn that into cubic meters, it's a big number. So even though there's not many per cubic meter, we have enough of them overall that we can still get an estimate of what that temperature is.
Let me carry that a little bit further.
Sure.
We're saying that the temperature is very high, but the density is low.
Yes. Right.
The particles are far apart. So we don't have much energy there. We don't have much heat there, but we have high temperature.
Thank you, sir.
Right. That's another way of putting it.
If I would take a piece of metal the size of like this and put it out there, it wouldn't get hot because there wouldn't be much heat around for it to absorb. There's so few particles that, although they have high temperature, there's so few particles out there that they aren't going to put much heat into this object I put out.
But there's iron out there too. We see iron though as dark dust.
Right. But the densities are very much lower than what we are used to here in the Earth's atmosphere as a local gas. So the amount of heat you have per cubic centimeter may be much lower.
So
But that's okay.
For us Earthlings that think of things the way we see them here on Earth, it's rather strange because you have lots of temperature and almost no heat.
And we were taught that temperature is the concentration.
But see, yeah, okay, so temperature is not the same thing as heat. Temperature is the degree of hotness, which is different from heat, because heat is to do with how much energy you have in a given volume. right? I think that's what you're getting at, yeah. Yes?
You drew a beautiful box with a forest inside.
Yeah.
30 million light years on the side. And you looked through that to a quasar. Any indication of how much dark matter was in that box?
That's a very good question. I can't tell you from an observational point of view how much dark matter is in that box. What the theorists can tell you, the people who make the simulations, is that in their simulations the gas and the dark matter sort of follow each other. So this is a picture of what the gas looks like. You'll find similar pictures of what the dark matter look like. But because it's so hard to observe, we can't tell you very easily whether that dark matter really does follow that prediction. So that's why I focused on the gas, is that we can see the gas, right? Yes?
These individual atoms that are 10,000 degrees, are they plasma then?
Yes. So the interstellar medium has regions that are neutral and a neutral gas, but it also has regions that are ionized. The stuff you're seeing in the hydrogen emission is neutral. The radio emitting gas that we see in the 21 centimeter tracer, the 21 centimeter line, that's neutral gas. But there are other regions of interstellar space that are seen by plasma transitions too. Yeah.
Is it really true that by far most of the matter in the universe is plasma, is ionized rather than?
Well, let me just be very clear, most of the normal matter, which means I'm not talking about dark matter or dark energy, which are two separate subjects, but most of the matter that consists of atoms, most of that would be in plasma, but I don't have numbers for the exact breakdown between gas and plasma. But the point I was making is that the solids and the liquids are much smaller in comparison to the gas and the plasma. Yeah.
But when you say gas, I usually think of gas consisting of nice little tiny atoms with electron clouds around them and all that, whereas plasma is ionized.
Right. That's right. So I might have been a little unclear about that. See, sometimes people talk about plasma as a type of gas. They'll call a plasma is an ionized gas. But now it's more common that you'll hear just plasma and gas treated as two separate states of matter. I mean, historically there were only three states of matter, so plasma was kind of tucked in with the gas. Yeah. Question back there? Yeah.
I was confused by your superposition of the Magellanic Stream on the Earth. It looked like the Magellanic Stream was about a third the size, roughly, of the large and small Magellanic Clouds. And then when you superimpose that over the picture of the Earth, it looked like the stream was about as big as a third of the circumference of the Earth. So are you suggesting that the Magellanic Clouds are only several times larger than the Earth?
No. So what I'm doing is showing how much space do they take up on the surface of a globe or on a map? In terms of angle, right? So you can look at what the surface of the Earth looks like on a projection like this, which shows you the continents. We can do the same thing in astronomy when we study the galaxy, and many different people do that when they look at radio waves and microwaves, is they put things on this galactic coordinate system. So the comparison I was just simply making was, if you had a gas cloud that covered the same fraction of the Earth's sky as this thing does of the galaxy, it would come all the way down from this continent across the South Pole and up there. So. Perspective, yeah. Thanks. And the yellow shirt? Yeah.
Yeah, a little bit more elementary here. If Jupiter is gaseous, why does it appear to be like a huge marble with various striations and colors? Where do the colors come from, I guess?
So Jupiter has its own weather patterns. So it has atmospheric circulation, it's rotating, there's energy that's associated with the planet moving around its spin axis once every day, every Jupiter day. And those weather patterns give you these bands that you can see in the colors of Jupiter's atmosphere. So, I mean, even though it doesn't have the solid surface the way the planet Earth does, it can still have weather. And that's what you're seeing when you see those
and it's
stripes.
opaque to the light. So it's reflecting,
Can we
it's
compare
reflecting
that to
sunlight.
simply, that say Jupiter is like star, it's a very dense gas?
Yeah, it's similar to a star in the sense that it's a spherical ball of gas. The difference is it's not producing its own energy in its core.
But it has enough density that you can't see through.
It's opaque, yes, right.
Has Jupiter been called sometimes a failed star?
Well, there are objects called brown dwarfs, which are failed stars. They're stars that don't have enough mass to ever get hot enough in their cores to start burning hydrogen and producing energy via nuclear fusion. But Jupiter is, compared to the mass of the Sun, Jupiter is much, much smaller. It's much less massive. So,
But hasn't they described the solar systems consisting of the Sun, Jupiter, and debris?
yeah, they have, right? And they've described Jupiter as the vacuum cleaner of the solar system because it's more massive than the other planets and it sucks up passing rocks. That's right, yeah. Yeah.
What is interstellar dust, and is it different from interstellar gas?
Yes. So I haven't mentioned interstellar dust. Dust is basically small particles. So when an astronomer says dust, you're not talking about atoms or molecules, you're talking about microscopic dust grains that can have different organic molecules in them, they can have silicate molecules. And they contain a very small amount of the mass compared to the gas, but they're still important. The dust does things like change the color of the starlight that's passing through it. So it's an important part of the space between the stars, even though it doesn't have much of the mass in it. It's
Which
particles.
category would dark matter be in?
The category of the four basic states?
The dust or the gas?
Well, it would be neither. Yeah. So I mean, we don't understand what dark matter is. So.
You said something earlier about it's made up of atoms, not like dark matter. You think dark matter is not made up of atoms?
Yes, I think it is not made up of atoms. Yeah.
Something completely different. And part of the reason we don't know what it is because it's so hard to observe.
But you're sure it's not an atom?
I'm pretty sure that it's not normal matter because normal matter produces light or absorbs light, and therefore we can observe it. Dark matter is so completely different that it doesn't react to light in the same way. It reacts to gravity. We can detect its gravitational effects, but we can't detect it by light.
Right. That hand has been up for a while.
What is the origin of the heavier elements?
Heavier as in heavier than iron?
Heavier than iron.
So there are other processes, they're called nucleosynthetic processes in stars, where you take a neutron and you keep adding a neutron to each atomic nuclei. So you go from iron to the element which is one above iron, and you can build up heavier elements that way. It's called something called the R process, for the rapid process, where you're building up elements one by one, starting from an iron atom and adding a neutron each time. But again, these are processes that are thought to happen in the cores of stars, where you need very high temperatures and you need high densities. So you wouldn't ever see something like that in the interstellar regions. It has to be in the cores of stars.
I've also heard it say that some of them are formed during supernovas explosion.
Yes, the type 1a supernova in the binaries, they can also synthesize new elements there. That's right. Yeah. Yes. And then afterwards I'll come here, yeah.
The gases we're familiar with on Earth, the confinement mechanism is largely physical volume, matter, and to a lesser extent gravity.
Yeah.
What is the confinement mechanism for interstellar, intergalactic?
That's an excellent question, and the answer is the same. It's gravity. So what keeps the gas in the sun confined is the gravity of the sun, is the mass of the sun pulling everything together. And what keeps the gas in the disk of the Milky Way, in that thin layer, is gravity, because everything is falling down towards the central plane of the galaxy.
Do calculations show that gravity completely explains what we observe in the confinement? Or is it, I mean, after all, that's how dark matter was discovered, that the gravitational because of the matter that we could see in the galaxy. It couldn't explain the rate of rotation and the distribution
That's
of
right.
matter in the galaxy.
Yeah.
So correspondingly, is there a discrepancy?
I'm not sure if you look at the height of the radio emission from the Milky Way, whether you can explain that from normal matter and the gravitational effect of normal matter alone, or whether you need dark matter. I'm not sure. It might be that you can do it with normal matter because it's close to the plane of the galaxy. The dark matter seems to be more extended. It goes out towards the outer regions, so you would need to be out there to see the effects of it. But I'm not absolutely sure. Yeah. Okay.
Well, that was the question. If you look at the Earth and you see the gases on it, everybody worries about them just moving and changing. Is there any observation to be what we know from the Earth, the impact of gases changing?
Well,
do we think it's going to disappear?
Atmospheres of planets certainly do change. We know that's happened. We can see that the atmosphere of Mars used to be very different than it is now. We see evidence for water on Mars in different, different forms. So atmospheres can change, but they tend to change on very long time scales compared to human time scales, right? So probably not something we have to worry about. That's it. Yes.
Another naive question, I apologize. You were talking about the hydrogen burning.
Yes.
Is oxygen involved in that, or what is the meaning?
When I say hydrogen burning, I mean the way that a star like the sun produces energy is it takes hydrogen nuclei, protons, and it fuses them together. It combines them. And when you do that, you make helium. Right. So, yes, so it doesn't involve oxygen. It's just hydrogen. And
energy is generated in that kind.
yeah. Now there are other nuclear reaction pathways that do involve oxygen. The one that I just talked about is called the proton-proton chain, that is based on hydrogen. There are other ones that do involve oxygen. But it depends on how massive the star is as to which of these pathways is the most, is the dominant.
It would be more proper to say it's fusion rather than burning.
Yes, it would be. Yeah, there's fusion reactions. Yeah.
Chemical.
Yeah. Yes.
In the announcement yesterday of the discovery of, I think it's called Kepler 10c, the megaplanet, that might not be the right term, the company story, at least in the Post this morning, described the sun, I believe it was a yellow dwarf. If the sun is a yellow dwarf, I mean, obviously there's some order of magnitude here. What would be the next larger magnitudes of other stars? Obviously there's an implication that there are larger stars or suns than our sun. So how would you describe them as you go up some kind of a scale?
Well, I mean, I guess you can call this a star like the sun a yellow dwarf because, I mean, the color of the sun, the wavelength where it emits most of its light is yellow, right? As you go to more massive stars, they become hotter. And when something gets hotter, the colors change. So you head up a scale where you go towards bluer stars. So, and then if you go down to the other way, you go down to less massive stars than the sun, you go down to so-called red dwarfs, because they're cooler and they emit red radiation instead of yellow radiation. So if you hear a red dwarf, it's smaller than the sun. If you hear a brown dwarf, those are the failed stars we mentioned before that are too low in mass to ever get any nuclear reactions going at all. Yeah.
When do they cease becoming a dwarf and are called something else?
Well, if they form a spherical object that you can see, people will call it a star, and a dwarf is the smallest type of star. If it doesn't form a star, then it wouldn't be called one. So, yes?
This is related back to a couple things ago about the formation of elements in stars.
Yeah.
So you mentioned that after, for things higher than iron, that neutrons will be added. Does the actual formation of the different elements, is that a result of beta decay? Because if you just keep adding neutrons, you're just going to have higher isotopes of iron?
Yes, so that's a very good point. You add a neutron, and then depending on what the half-life of the newly synthesized nuclei is, it can beta decay to a different nuclei. And then if that one adds a neutron, you can start a new pathway going up from there. So you're right, the beta decay where an electron is released is a very important part of that too. It's not just the addition of nuclei. That's right. Yeah.
One story I've been seeing too is a lot on the gravitational waves that they found that was supposed to correspond with Einstein's findings. And then they found out that they didn't account for the interstellar
dust.
I forget if it was gas or dust. Yeah. Could you talk a little about that? I didn't really.
Yes, I can try to. So that's a big subject. So there's this experiment at the South Pole called the BICEP experiment, where they looked for polarization of the microwave background. I talked about the microwave background quickly in this talk. They found that for the first time a particular type of polarization signal in that microwave radiation, and that polarization signal is exactly what you expect if you're seeing the signature of what's called inflation. Inflation is something that happened very soon after the Big Bang, where the universe went from being very small to very big. And it left a certain signal in the microwave background, which they're claiming they've detected. Now, since that announcement, there are people that have claimed that the signal they're seeing may be somewhat contaminated by dust particles in the foreground, in the Milky Way. I think that question is not 100% resolved. People on the BICEP 2 team may still claim that their results are valid, whether or not there is dust there or not. But I think we're waiting for the latest dust maps to come out, where people have looked at these foregrounds and can very carefully map how they change with position. And then after those updated dust maps come out, then we'll see if the BICEP results still stand.
So it's basically just the dust changed the polarization of the signal?
Yes, so dust grains can change the color of starlight passing through them, or any form of light passing through them, and they can change the polarization of light passing through them too. So they are something that have to be understood. Yes. Yeah.
I worked on a space track radar down in Florida, and whenever you sent our radar signal through the ionosphere, the polarization would just rotate, going, and when it reflected, coming back, it would rotate. So we had to have cross-polarization at the radar because we didn't know what polarization was going to be when it got back to you. The ionosphere really does rotate the polarization of radio waves.
Right. So when they do polarization measurements, they have to use more than one frequency, because if you have more than one, then you can figure out what the effect is rather than something else.
Well, we had antennas that were polarized this way and this way, so we would just see which is the largest one. Which one did we get the most in? Because that's what the polarization was when it came back.
Yeah.
You know?
Okay.
Is there a question back somewhere there?
Yeah, going to the pulsar experiments where you're looking at the distant spectrum, are you looking at the gas through teasing out the redshift effects?
Yes.
And so you're looking primarily at hydrogen, and you're getting the closer gas and the further gas clouds by looking at the redshifts.
That's exactly right, and I didn't go into detail on that just for reasons of time. But if I put this quasar absorption line slide up again, let's assume that this light, this line that's being absorbed is a hydrogen line. Then the only difference between these three clouds is how far are they moving away from you. So this one is the most distant. That means it's going to have the highest redshift. So the line appears closest to the red. And then this cloud is less distant. It gives you a line that is here in the yellow part of the spectrum, whereas the cloud that is closest to the Earth gives you a line that is in the blue part of the spectrum.
And in general, when we're talking about these clouds, we're talking mostly helium and hydrogen.
Mostly, but they do have metals in them too. When I say metals in the sense of heavier elements. Now this is a simplification in that I'm just showing one line. Hydrogen has more than one line, it has a whole series of lines. But having that pattern of lines helps you to identify which redshift something comes from. So you have many different fingerprints that you use to identify the chemical elements and how far the clouds are moving away from you. So this is a simplification where I've got one element and one line. Real clouds have lots of elements with lots of lines, giving you complicated spectra that you need to analyze.
So how many clouds do you actually measure? Imagine what it's 10 or...
Well, if you look at one of these, this is a Lyman alpha forest spectrum, probably something like 50 lines there, and that's just in this, and this is only a small portion of the spectrum that I'm showing here in the rest frame ultraviolet. So it depends on where you're looking. There's huge numbers of lines you can look at in the infrared, in the optical, radio, different parts of the spectrum.
Okay, so it sounds like we're done here. Thanks for coming.